Hi there. I want to start today by just reviewing our learning outcomes for this course. First and foremost, the idea of this course is to give you an understanding of a microcontroller-based embedded system so that you develop a picture in your mind or a mental model of what's actually happening inside a piece of equipment. So far you've looked at turning on and off LEDs, so when you look at a washing machine or a dishwasher or some other appliance and you see LEDs going on and off, you should be starting to make those connections now with how these things actually work inside. So I want this viable mental model. I really want it to be a usable idea of what's happening so that you look at a new device you've never seen before and you can begin to imagine what's happening inside it. One of those things that's really important is the interrelatedness of hardware and software in an embedded system. And we've looked in detail at how the macros are used to actually test and check bits in a register and how they're used to set and clear bits in a register. And we've looked in detail. So if you think about the success criteria now for those, explain how program commands work that link hardware and software, how registers work. Can you actually explain that now? How those bits are set, or how those bits are cleared, or how those bits are checked. And of course, this requires your understanding of your Boolean identities. Now also, if I gave you a data sheet, you're not too familiar with them yet, but you will be getting more familiar with them. And I asked you to set or clear or check a single bit in any register in the microcontroller. Could you write the code now to do that? So these are the sort of success criteria. When you're able to do those things, you understand the interrelatedness of hardware and software in embedded systems. Do you realize that an embedded system is an automaton and that it basically operates without any intervention from you, the user, once it's going? You know, in a car, you don't need you turn on the key, you don't need to turn on the engine control unit. It turns on automatically for you. So that's an automaton. And how did you do that? Well, we turn an embedded system into an automaton by using our while one statement. Can you explain state? How the past and the present influence what's going to happen in the future in an embedded system? You cannot ignore those things. They just are part and parcel of what's going to happen in the future as what has come beforehand. Whereas a PC is much more transactional in nature. We're going to go on now and have a look at the reactive and responsive nature of an embedded system. An embedded system must meet the requirements of its environment. It's no good to us if it's not fast enough or doesn't check things fast enough, or if it's too slow to actually drive things in the environment and be seen and be useful. And so we need it to be reactive and responsive. And so we're going to go on now and through our notes, I'll page down to where we're currently up to. There we go, and we're on page 121, which is describing the embedded system as reactive and responsive to its environment. Now, if you have a look at this, this is one of the questions in the assignment. This is the question to do with the pedestrian crossing. How do we make a pedestrian crossing reactive to its environment? Well, basically, we have a switch on a pole that a user can press to make it do something. And so that means that we have to be checking the switch consistently all of the time to see if it's been pressed. And that's how we make it reactive and responsive. Also think about a more complex system like full traffic lights where you've got sensors in the road and you've got multiple directions that people can cross in different systems, and so it must be able to measure and detect traffic flows, perhaps whether there's a vehicle sitting or stationary over one of the sensors in the road, or whether a pedestrian has pushed a button. Think about some of those really complex not pedestrian crossings, but those traffic light systems that have multiple inputs. To be reactive and responsive, the system has to check them all the time. So how does this happen in software? Well, what parts of this code are really important to checking to see if our system is responsive to its environment? Well, the first thing is we've got to check the switch. So this is how we check the switch. We have an if statement, and of course we have a closing brace to our if statement. And if the switch is pressed, then do what's inside the brackets, the braces. Otherwise, if it's not pressed, don't. And you understand now how this line works in terms of its Boolean identities to checking bits in a register. But what else is involved up here? Well, first of all, we have to define what this macro is. That's really important. Another thing that's, of course, important is activating our pull-up resistor. If you're not going to use an external pull-up resistor, then we need an internal one. And I'll go into this in a bit more detail. What else is involved? Well, actually, one of the core components of this is the fact, that it's inside a while loop. And without this while loop, it cannot be reactive to the environment. It must check the switch regularly. And the word we use when we are checking the switch, so checking the switch is actually polling. And we're going to go into this term in more detail. So checking equates to polling the switch often. How often? Well, often enough is the right answer for whatever the environment is that we're doing things in. Let's go down, have a look at the actual resistors and the switches to see what's happening here. It's really important to understand that a system can't be reactive and responsive to the environment unless its input is stable and consistent. And this is what it's really all about here. And that's why this pull-up resistor is a critical component in our system. Without it, our input will not be stable. Let's have a look and see how it works. So at the moment the switch is open, so if our VCC potential is 5 volts, that means that there's 5 volts to our microcontroller. If you're thinking about this in terms of a voltage divider, that's a really good way of looking at it. At the moment this is an infinite in voltage, an infinite resistance, and in actual fact the input resistance to the microcontroller is fairly infinite as well. So this voltage here will be 5 volts or a 1. Of course, when we press the switch, what happens is the voltage divider, this becomes 0 ohms. And this now, instead of being sitting at 5 volts potential, sits at ground potential, which is 0 volts. So what we've got is not pressed and pressed. So this is our active low. In other words, it goes low when we activate it. Now, without the pull-up resistor, it would be floating. This voltage here would float, especially in this situation where we've got if we took away this pull-up resistor, then this line here would be floating in the atmosphere and susceptible to any electromagnetic fields which are around it, and it can actually drift in value between 0 and quite high potentials actually. And you can test this yourself by actually building a little system and waving your hand around the pin, and you'll see that it'll trigger the system and trigger the software, because it will fluctuate between 0 and high. Now, of course, you understand now how to check to see if the switch is low, and you understand now how to check to see if the switch is high. There is an alternative, of course. You could have a pull down circuit, not so common, but you could do it. And what that means is that the input pin is sitting at ground potential until you close the switch, at which point it goes high, which means that when you close the switch, it goes high, so it's an active high system. Not common, but now you know it exists. Next thing I want to have a look at is what we're doing when we're using functions in a piece of code. And I think it's really important not just to think, oh, we write functions, but why do we want functions? And really the whole thing about functions is really to make our code more transparent to other people and ourselves in the future, so that we know what we've written and can understand it. So to do that, functions typically have a single purpose. And each one of these functions here, like the functions, I've got a 1, 2, 3, 4, 5, and 6, and each one of them has a single function, which is to turn on a particular set of pins on the microcontroller. And you can fill this in on your own in the question in the assignment for yourself, because your configuration will be different to everybody else's. Now, having a look at functions, we typically put the functions at the end of the program, which means that we have to have prototypes for functions at the beginning of the program. In this case, I'm not returning any values from the function and I'm not passing any parameters to them. Another thing about functions is that they have descriptive names. I've labelled these 1, 2, 3, 4, 5, 6. Is that a satisfactory naming convention for this program? Well, this program is pretty much it's a trivial program. All it does is it counts a variable 1, 2, 3, 4, 5, 6, and when you press the switch, it puts that count value onto one of these and calls one of these functions depending on what the value is. So really, it's good enough. But if you're in a bigger program, then you might want to give it a more accurate name like display1, display 1 on LEDs, something like that, for instance. So you might want to give it a more descriptive name. When you're writing these functions, these are very small functions, of course, they fit on one page. It's a really good idea not to have a function which splits page boundaries. Makes it much easier to see what's going on. I've already mentioned that you use function prototypes, and that just makes your code tidier by putting all of the function stuff after the main loop. And of course, once you get into bigger programs where you have header files and you have functions which are in other files, then you use prototypes and call them via the header file. Now, another thing here about functions is that's really important, and that is that they decomplicate your program. So they decomplicate your program. This is really important. When you look at this, oops, sorry about that, they decomplicate your program. When you look at this code, I could have put this lines of code here, up here, in the case for 1. Now, it would make it, well, it would still probably all fit within one page, the whole program, so you could do that. But the whole idea really about making your code transparent is to get rid of the functionality from inside this sort of main loop and just have big abstract ideas. So really using functions is a really important part of doing that. So we even if they're a small function, we tend to put the detail into the function, even if it's just a little one, and then use the function call, okay? Right, let's understand. Oh, now more about transparent code software practices. Really, it's such an important thing that you really get on top of. We don't want to have your code looking like a can of spaghetti when someone opens it up to have a look. Huge problem with doing this. So what do? Well, over here we use a template for our code. That's just a nice structured way of writing code. If you go and work for someone in the future, you might find that they have very definite ideas about what goes into the template. It gives structure to your code and puts code in different sections. It's great to have a title block at the beginning of your code. Okay, up here I've got the project name. This is from the Cylon 14 program. I wrote it back in 2014. Okay, it's version 1, and this code ... gives an explanation of what it does. Macros. Okay, macros are one of the most important things in your code. Okay, if I have this macro, here it is, here hash defined time delay is 100. Here's a really important one. Down here, I could have put 100 into each one of these calls to the delay function. Now, the reason that I've used time delay is it makes it much easier to understand the code, and it makes it much easier to modify it, because if I want to change my time delay, all I have to do is change it here. I don't have to go through and look for every place in the code where I've done it. And so that's why it's really important not to use things called magic numbers. So if I put this 100 in here, then this becomes a magic number. And magic numbers are really hard. You come across this number in your code and you think, well, what's the purpose of this 100? Why is it 100 and not something else? And so that's why it's much better to call it time delay. So we don't have magic numbers in our code. And with macros, the convention is to fully capitalize it. No lowercase. Okay, variables have got lowercase, functions have got lowercase, but these macros are uppercase. Now you'll notice when you run this program, and it's just something I want you to think about and look at the next time you're running one of them in the simulator, is that the first thing that you do when a program is run is the preprocessor replaces all of these names with the actual values. And you can see that in my simulator. That's one of the aspects I built into it, is so that when you push step the first time, all of these macros disappear and the actual number appears in there. Have a look at that the next time you're running the simulator. Comments. Okay, here's the big one that a lot of people struggle with. These are here to describe the function, not the syntax. Okay, I can tell here what this is doing. What it is doing is it is writing 1 into every bit of data direction register B. But that's not an explanation of its function, that's an explanation of its syntax. So what I've written here is an explanation of its function. It's set up all pins as output. So that's its function. That's its purpose for being here in the code. And that's the sort of thing you write into a comment. If this comment is completely self-explanatory, then there's no point in writing the comment at all. So take down here, for instance, port D equals this. Well, actually, what that's doing is it's setting bit 0 in port D. Okay, that's its syntax. But that's not its function. It's turning on the first LED. Okay, that is what it is doing. This is turning on 2 LEDs. This is turning on 3 LEDs. This here is actually moving the pattern left. Okay, can you see what that comment is saying? It's not describing the syntax at all. What it's doing is it's describing its function, its purpose for being in the program. And when you're writing this, you need to think about it in terms of the system perspective. What is this line of code doing for my system, my embedded system? Okay, layout, incredibly important. Again, what we've got here in terms of layout is we've got all this nice indentation. Okay, that's really crucial. Syntax highlighting is something you'll find that is done by your editor. Well, why are these points so critical? Well, engineers are not haphazard in what they do. Professionalism is what it's all about. You know, and documentation is really important. And organisations will have their own formal methods of structuring their planning and documents. Don't turn up your first day of work and say, well, I'm going to do it my way, okay, because you won't last long. In an organisation, they have their own way of doing things. And if they haven't, then maybe it's not the sort of organisation you want to work for. Here's an example, right? Here's the same pedestrian crossing program, but what I've done is I've removed all this indentation. In fact, I've made it so that none of this code is indented, making it hard to spot errors. Yeah, even my sentence there without spaces says it all, doesn't it? Can you spot the error here? Right, have a look at it. Now, can you spot the error here? One of these lines of code is actually incorrect. But you can't see it very easily because we've done things like we've put in ways to directly control a pin on a port. Well, what is the point of this? It doesn't tell me what the purpose of this line of code is for the program. It makes it really hard to modify. And of course, here's my magic number appearing 3000. So have a look at this, see if you can figure out which one of these lines of code is incorrect. Now I want to go on to a really important aspect of programming. And this is really about making it, we're coming back again to making the system responsive and reactive. And I've already mentioned the word polling, and so what we've got here is we've got a little quiz game controller that someone's made. This is not one of mine, it's off Instructables. I'm going to show you my one. So you've got 4 buttons, and when you press one of these buttons, the LED comes on for that particular user, and at that stage no other user can press their button and their light will come on. It won't activate their light. And then in the middle of this you've got a reset button. So what I've got over here is I've got my own version of this made, and it's a little bit hard to see the colors in this because of the fact that this is a webcam recording it. But what I'll do is, first of all, I'm going to press, say, the blue button, and so my LEDs are lit up blue. Now you can't really see the blue very well in this because of the nature of the webcam, and you can just sort of see around the fringe of that they are blue. But of course, if I press the green button or the red button or the yellow button, that won't change. But if I do press the reset button, the LEDs, well, they all blink in a nice little fashion and then they go off. So this is how it works. If I press my green button now, you can see a bit better that this is green, that shows up a bit better than the blue did. But I've pressed the green. I've also got a little green button on top of my switch here, and the other ones lock out. Okay, so I'll just reset those again and just show you this one more time. Let's use the red button. So yeah, you can see that this is a little bit better, the red. You can also see that the red light is lit on this to say you've won. Now, the idea is that it's polling all of these 5 switches consistently. They're just running through a loop, polling all of these switches. And you can see that in the program. And when you press one particular switch, what's going to happen is, if I say press these 2 at the same time, you can see the green one actually came on. So the green one came on rather than the blue one. And so if you've got 4 contestants hovering over their switches and they press them, well, that's the blue one came on. So there's the blue. So what we've got now is a system that allows the first person to press their switch for them to lock out all of the others. And that lockout is really important in this. No one else can press their buttons. So let's just go back to this code. And what we're going to do is write, well, I haven't written an algorithm here. I'm going to get you to write the algorithm, and you've got to write the program to solve this. But basically the way the system works is initially the lights are all off. If a switch is pressed, turn on that contestant's light, lock out all the other, well, lights is probably not the right word, but switches, so that no other contestant's switch press gets acknowledged. Okay, so if the reset switch is pressed, then turn off all lights that are on. Okay, so now that's a bit of a description of an operation of or function of the program, but it's not really an algorithm. You've got to piece this apart and think, how do I turn this into an algorithm? And the way this code works is it checks each switch. So you're going to have a bunch of if statements, if, and then you're going to have another if for the next switch, and then you're going to have another if for the next switch, and then you're going to have another if for the next switch. And then of course you're going to have an if for the reset switch. So you've got a bunch of if statements inside your while loop, and then your while loop will, but you've actually got to think a bit more strategically about this in terms of figuring out how is this going to work, because I have to lock out the other switches or not test the other switches. And a lot of people get a bit tied up with their logic here, putting in lots of if statements or things like that. There's a fairly straightforward way of doing this, and the only hint I'll give you is it's really useful to use a variable at this point in your learning. Okay, just to round off this little bit about using switches. Switches are mechanical devices, and when you get someone pressing a switch, there's a little spring, and then there's a little metal plunger which comes down and hits these 2 metal contacts to make a connection between the 2 of them. Similarly, we've got this tact switch. Now these tact switches are much better mechanically. This number 3 here, this item 3, is a little metal dome. And so it's not just a flat disc, but it's actually raised slightly, and it acts like a click, and that's why you get a nice little sound and a solid click when you press a tact switch. And that means that when it comes down and joins the contacts, which are inside the body of the switch here, it has a really good solid connection. When this one comes down together, what happens, no matter how fast or hard you press it, the two metallic objects come together and they bounce for a very short period of time. In fact, there's a neat little YouTube video here of two solid objects coming together and what happens when they do, and they bounce, okay? And this is called switch bounce, and it's really an important thing that you need to come to understand. There's some interesting videos around on it, but basically, if your microcontroller is seeing, and when I say seeing, I mean it's polling at a really fast rate. It's checking your switches at a huge rate of time. Like our microcontroller is running at 16 million cycles per second. So it can check a switch, or if it's got 5 switches like our quiz game controller, then it might be checking those switches 1 million times per second. And if a switch bounces like this, then it can actually, it might detect multiple bounces. And there's a really big problem in electronics because microcontrollers run so fast. And so what we do is there are ways electrically that we can get around this, and one of the simplest ways is just to put a capacitor across your switch. The explained mini board is one of the development boards I've mentioned earlier. They put a little 0.1 microfarad here. Another way, of course, is to use some sort of flip-flop connection. This is quite good. This will stop a lot of contact bounce from happening. And there's a very good, reliable system here. For those of you who are doing electronics and learning about diodes, this is a nice little circuit to unpick its meaning behind. So yeah, again, there's a capacitor here across the switch, but the time constants vary depending on whether it's pressed or released. And often we'll use a delay in a bit of code, just a very brief delay, something like 20 or 30 milliseconds. Okay, so I'm going to stop this video here, and yeah, hopefully this has been informative and interesting to you. Cheers.